Well, as you see, I went through all the graphic statics um, solutions, and I'm not sure this is really the best represented. I mean, that the numbers are really correct because actually I didn't. The one thing I didn't check was the actual sizing of the members. So if a couple of people picked the wrong member and got their weights a little wacky, that's because some of them look. I'm a little bit surprised of the order of it. Also, there were a couple of them where the probably accidentally changed the well, on this first one that seems to have done the best. I mean, these are in order of lightness, right? From 423 all the way down to, what did we get? 728 was the heaviest. And actually, these look pretty close. I mean, this one and the best one are not. I mean, this one, the odd thing about this one is David lengthened it, probably by accident, but it's stretched 2 feet on either side. So instead of being 32, I guess it's 34 feet wide. And you would think, okay, that would be to its detriment, right? It's got to make it heavier. It certainly lengthens the members, but somehow he also raised the height of it, and maybe in raising the height, of course, it reduces the forces in the members because it's just like a beam. You deepen it, and it reduces the stress in the. I mean, it doesn't change the moment, but it reduces the stress in the extreme fibers. Well, you're reducing the stress or the force in these extreme fibers when you deepen it. So, okay, that helped it. And I don't know, maybe stretching it out got better angles for these. Somehow that one came out as being pretty light. This one I thought was more believable, but also pretty low. I mean, not very deep. These, I can imagine, this would have been my anticipation, that they are more parabolic in shape, right? Which would follow a moment diagram. I mean, they are, after all, essentially a beam, a reticulated beam. So, okay, that would be the ideal shape for a solid beam to follow the moment diagram. So, okay, that kind of makes sense to me. Where was the other one? Oh, this one was very, very interesting. Cheated a little bit because it changed the topology. If you look, and it took me a minute to realize, the beams were, I mean, the members were originally going this way, and here it's switched. It flipped, and that was actually a better design. I mean, it seemed to work better because it also flipped. Look at this. This is, here we usually have the higher stress on top. Here would be a good comparison. 10 versus 9. Oh, those are pretty close. But usually the higher stress, sometimes it was in the 20 kips or something, or 15 kips on top, and then less on bottom, which is kind of reverse of what you would wish. If they're not going to be the same, the tensile force, since it's not buckling, would be nice to have that a little higher, and the compressive force that's got to withstand buckling be a little bit lower. When he flipped the diagonal here, that's exactly what it did. This is 24 on the bottom and 16 on the top. Interesting. Interesting. It's still compression all the way across the top, of course, but now this flips from here. It was in they were in tension, I guess, right? Which makes sense if you imagine it, that panel. I guess it makes sense. Wait a minute. No, it almost doesn't make sense. That would go like that. Yeah. Oh, that they're in tension. Yeah, I'm almost surprised that's in tension. But here it flipped to compression, but not a pretty low value. So, okay, interesting. But then, of course, this one goes 0, and that one picks up a little bit of force. I don't know. Hard to totally follow the rationale of these. These then look a little bit more the same, kind of a group here. This one was awfully deep. This is yours, right? Yeah, this one was probably, what I would have guessed the right shape, but maybe it got too deep. It's because the forces are pretty low. As you make it deeper, the forces go down. So that's the right direction. But the trade-off is, of course, the members get longer. So it's a tricky balance. The other thing that it really wasn't controlled in this problem and made a difference, as these, like in yours, let's see, 1, 2, 3, 4, yeah, it was slightly shifted to the sides. That load, right? The position of the load is changing. Originally, they were 4 foot on center. They were there. 8 foot, I guess. There and there and there, and then in some of them, yours changed a little. That one changed even more. Alex putting it out to the side, and that should. Oh, yours are down toward the bottom, heavier ones. It should reduce it, because you're reducing the moment, right? If you can imagine, if you could get those loads all the way to the supports, they'd be not really putting as much load on the truss. But I guess the price you pay for it, at least with Alex, is this gets very long. So that probably, I didn't look at the size of that member, but it's probably a pretty heavy member right there. And a long member. So, yeah, that's maybe the trade-off. So there were a couple of things that, aren't really totally controlled with this. As far as a realistic truss, really, these loads, if they're coming from if this is a roof truss and it's coming from some sort of surface load, they should vary as you move them, right? Which we just kept them constant. So that's a little bit wacky. But at least you get, the point of it wasn't really so much to optimize it as it was to see how that graphic statics thing works. So you can get at least a little bit of a sense for that. And the pluses and the minuses of it, you can see it does allow you to graphically control the forces, but it's very difficult really to see the reciprocity, how that then changes the shape, because you're changing the angles, and it's hard to really see that. There's a friend of mine at Delft. It seems like I asked him once before, but I don't remember getting it. He wrote a program. It seems like it was like a Grasshopper script or something that actually connected the two, so that you could sit there and move the force diagram and see it change on the truss instantly, and that's pretty nice. Then you get a better interactive sense of it, and that's maybe a little bit easier tool to use. So yeah, that would be maybe another route to go if you could get a hold of something like that. Anyway, so that is as much as I think I'll go through with that. Let me see if can I shut that? Okay, and then let's see if I can. So what I thought, I came up kind of with a extra lecture here at the end, which is nice in a way. And I thought what I'd do is, as long as we're kind of on the topic of optimization, I mean, that was, I guess, years ago, the topic of my dissertation had a lot to do with optimization and developing a genetic algorithm program, actually, that made use of that. So I thought I'd go through and give you a little bit broader look at optimization, different techniques, and focus maybe a little more at some of them that I've used, the ones that are using genetic algorithms, which seem to be the more utilized ones now. There are a lot of programs out there that either combine with Grasshopper or different things that will generate a parametric form and then optimize that in some way. But to start, I thought I'd look at a little broader scope and maybe the different types of optimization. The first question, even before you get to how you want to optimize it, is the question of what you want to optimize, right? Oh, let's see, I bet I don't have my pen on here. So what you want to optimize, and usually we think of optimizing the geometry or the topology, but also, of course, material, the member size itself. There are a lot of problems that just, given the frame, what would be the optimal member size, and some of that can, if it's an indeterminate shape, changing different member sizes affect other members, so there is a certain balancing that goes on. And then the methods, then we'll look at a few different methods. So as far as material, of course, the weight, using aluminum versus steel, if you're just trying to optimize weight, might be an approach, or, to change the volume, minimize the cost is, of course, optimizing the cost is a very common goal. Or you might want to increase strength, elasticity, ductility, stiffness. So those are, in terms of material, what you might consider. Member, of course, again, strength, stability, if it's in terms of a compression member particularly, serviceability or connections. These are things you might look at trying to, basically in design, we're always optimizing, right? We don't deliberately design something to be oversized. We try to, when you select a member or you select something, you try to get it to be pretty much the right size. Okay, now in terms of the overall layout, there are two things, geometry and topology. So there's a distinction between the two, and you can optimize either or both. This would be topology. The distinction between them, if you haven't really thought about it, geometry, you've got the same connectivity, right? I've got the same number of members, and the incidence, I guess is what you call that, the connectivity from one to the other, it's exactly the same. So all you're doing is, and this should have been what we were doing with the graphic statics, all you're doing are moving the joints around, right? You're just shifting the position of the joints. And there's a lot in that, right? You can see there's quite a large variation that you can get just moving the geometry around. Topology is actually gets into the connectivity, the number of members, and how they interconnect. So, whether I take this member and reverse it, right, flip it around, that's changing the topology because I've changed the connectivity of it. Or if I add members, right, or even more members, that's all changing topology. And of course you can see topology always includes geometry. So if I'm doing a problem where I'm optimizing topology, I'm usually optimizing geometry at the same time. So first I have to pick a topology and then optimize it to get the best geometry for that topology. So that kind of optimization is much more involved than a simple geometry optimization is fairly simple because there's less variation. Enormous possibility or variation with topology, and each one of the topologies has a whole range of geometries that you need to optimize. So there's quite a jump in scale going from geometry to topology. Okay, as far as methods, fundamentally, we can look at physical methods versus computational. Physical methods for centuries, decades were the ones that really dominated. People would, even to test things, would build something or build a model and physically test it. This image over here, this is Friato's model of the Mannheim Hall, the grid shell at Mannheim. And when he did that, that was 72. There were not a lot of computational options available. I mean, this is early days of finite element. I mean, it had been around, but on the scale of something like this, that's a lot to expect back in this is before you had any sort of desktop computer. You're talking about a mainframe and programming it specifically to do that. And so when he started this project, he started building models and he actually, you can't probably see it in this illustration, but he actually put gauges on those wires. So he was measuring the force in the wires and looking at different configurations and balancing the force and trying to, not exceed what the capacity of the members was going to be. Well, as he was doing that, Klaus Linkwitz at the same time was also at Stuttgart, worked on a finite element analysis of the whole thing. And in the end, he took the final result and analyzed it, was able to analyze it with the finite element. But the optimization, the finding of the form, was actually done with models. In terms of computational, the older method is linear programming, which is generally called the simplex method. And this is, you have to describe all the variables in terms of equations, linear equations. And those get drawn. I mean, you can imagine them plotted, and it bounds a space of acceptable solutions, and then you optimize that. In that space, you can, well, I'll show you, there's a graph of it in a minute. You can optimize it like that. But that's not always so practical because you have to put it all into equations, which if you have a discontinuous function, that doesn't work. Like our little problem with the truss, the sizing of those members was actually discontinuous, right? You've got a 4x4, and then suddenly you'd have to jump to a 4x6. There's no linear progression between the two. So it's not like you can pick any size. It's a step function, right? You got to pick the sizes that are available. Then there's a sensitivity analysis, homogeneous, which we'll look at, and then the stochastic methods. And these include the GAs, the evolutionary system, simulated annealing, swarm. So all these are kind of used now. Evolutionary strategies, not so much maybe now, but it's almost the same as GAs. Okay, so here a few quick examples. Physical, this was Otto's, the 72 Olympics. Oh yeah, the Mannheim was earlier. Mannheim was in the 60s, and it was before this. This is a model. This is a different model. This is that model. And there he also developed a complete model and did the measurements on it, and found the best geometry, the best overall shape of it with the model. Okay, or things like this. I think this was a wind tunnel wind tunnel models that can be changed. The difficult thing about the modeling, of course, is it takes time. You got to physically build the model. And if you're particularly something like a wind tunnel test, you build one model, you test it, you get the results back, and then you go, okay, let's change it. And you change it. Yeah, I mean, you got to go back and change it and then retest it. It's not quite like a computationally, you could do it maybe a little quicker. These are form-finding models, catenary models. I think I brought one in, back when we talked about grid shells, didn't I bring the catenary model in here? So that's a way to find a pure compression shape, maybe. Soap film models they use to find pneumatic shapes. So those, there are physical models. Analog models. This was one that used to be popular. It's probably pretty much died out. That's if I can even remember the name of it, photogrammy or something. Photogrammy or something. I forget exactly. But if you take a piece of plastic, plexiglass, and you project parallel light through it, and then stress it, bend it, you will get the pattern, the stress patterns. You can see the stress patterns. So this was a way to actually visually see stress patterns in a shape. And of course they do it with more complex machine parts generally, that you are trying to minimize stress concentrations and whatnot. So that would be one way. It's analogous because you're not testing the real thing, you're testing an analogous plexiglass model of it, something like that. Okay, and then computational methods. These are, this is what I was talking about with linear programming. You've got to take each variable, or each, each thing that you're optimizing, describe it as a linear equation, graph that. This is then the solution set, and then you find the best solution based on whatever criteria you have. You've maybe plotted this in a way that this is maybe weight versus, I don't know, something else, and this then gives you the lightest weight solution. You can find where that occurs. So that's a direct method. You get immediately the solution, and not a bunch of solutions. And in a way that's good. The downside is you have to actually describe everything as linear equations, which may not really be possible. So you end up fudging that a bit. The other problem is if you get that one solution and you look at it and you say, oh yeah, but that won't work because some other reason that's not included in your other criteria, and then suddenly the whole thing's trashed. There's no fallback solution, right? It's that or nothing, basically. I guess maybe you could try to find other solutions in there, but it's not a very flexible approach. Sensitivity analysis, this was an early method. Eckhart and Rahm used this a lot. You have a field, and it's like a plate, and you apply the forces to this plate, but the plate is composed of a lot of little elements, and you can see which of those little elements. You're essentially plotting the stress paths through the object, and it does it like it's almost like in Photoshop where you use the sharpen function. You sharpen, and it kind of reduces reduces it down into black and white, which kind of gives you these members, right? But in the end, it's you still have to kind of decide where the members are, and a lot of times they're coming out in ways that, I mean, okay, was that supposed to go up there? It's not a precise solution. It gives you a pattern that is would lead you to a solution, I guess. And then there's the evolutionary strategies. There are two. Originally, there were two approaches, and this is because they developed on different sides of the Atlantic independently. The Germans developed evolutionary strategies. Reichenberg and Hans Paul Schwefel were working on those, and they had absolutely no connection with John Holland, who was actually here at Michigan. He was at the University of Michigan and developed genetic algorithms. And after about, I forget how long, 5 or 7 or 8 years, it was quite a time, because the Germans published, Reichenberg and Schwefel did everything in German. It was not really internationally published, and they hadn't read Holland's work. Eventually, they did meet up and realize that what they were doing was very, very similar, and it kind of got combined into, now we generally use genetic algorithms, but this is originally the way the evolutionary strategies worked. There are a couple of different forms, either one at a time or two that would be, but it was also similar to, they didn't call it genetic, but they saw it as the variables, and the variables would evolve into by crossing essentially the same operations that Holland was using. So that was that, and what Holland was produced with the genetic algorithms, he patterned it very much on the idea of genetics, and was looking at. But it wasn't supposed to really mimic genetics. It was just genetics was the inspiration for it, really. So he'd look at, different forms of crossover. So if you cross these two, then part of this one would come down here, and part of this one would go up there, and you'd get this. And then what those genes are describing or the chromosomes are each, I guess what you'd say is each gene on the chromosome is a different variable. So you have all these variables that describe your problem, and they vary. The variables vary, and when you put them into something that generates the solution, what the composition of those variables produce different solutions, of course. So you're trying to find the best combination of variables to produce the best solution, and this is just ways to find different variable combinations, and the genetic methods or the just plain mutation, and in the end you also have to select which are the parents, right? And that selection process is part of the game, because you generally select the better ones. If you're trying to get better and better solutions, you keep selecting better ones. So these just show different methods of the approaches to crossover, flipping it. There were a whole bunch of different strategies that you could use for those, and depending on the problem and the variables, they'd have different effects. Or this was one that I used for a while for trusses, half uniform crossover, but you'd take, it's half because these two parents are coming down, and this parent is, and this would be selected randomly, would select half of the joints. So I select this one and this one, these two joints, and they would get crossed. And by crossing them, I don't just average them. I take a field around them, and that's the variables are being you're looking like this, and there's a a range to it, and you pick somewhere in that range statistically. So it might actually even fall here, but it's a higher probability it'll fall somewhere in the middle, and that then becomes that joint, right? And this one becomes that joint, and that's the new child. So you're creating a new child, in this case 2 children, because the other 2 joints went the other way. Whoops, I get the wrong one there. That was the top one. I can't even see which one's which. Okay, that's that one, and then this is the bottom one. So you cross certain joints, you produce, it's all just a way to generate a new solution. But the new solution that's being generated is based on these parent 1 and parent 2, right? So these new solutions are derived from the earlier solutions, and if you keep picking the better solutions, the idea is it evolves into a more optimal design. Okay, so this is what we've been doing here at Michigan. There's, oh gosh, this has been going on for 15 or 20 years, I guess, close to it. So there's several doctoral students that have worked on this, and this image here was actually in wood. This was a wooden grid shell that we did a few years back, and we actually did build part of it. Didn't get the whole thing built, but we were looking at optimizing the shape of it, and it was, interestingly enough, it was optimized for, it had to have a certain head height, and it had to have certain joint characteristics and whatnot that got optimized. Okay, but I'll give you kind of an overview of this method. This is based on genetic algorithms, but it's supposed to be specifically oriented more toward design discovery. So early phases of design, not the final optimization at the end of the design, but the beginning, when you're trying to explore different possibilities. You have a lot more flexibility. You can have much more impact at the beginning of a design. You have much more, that's what this is supposed to, in your creative freedom at the start of a design is much higher. I mean, you have, the possibilities are endless, right? But as you work on it, you make more and more decisions. Every time you make a decision in the design, it limits the possibilities till you get down to the end, and there are very few things that you could change, and there the optimization may just be selecting member sizes, or it may be much more fine detail, not the overall scope of the project or the. Anyway, okay, so that's, and in this process, it's a series of, I mean, it's iterative. You're all, how design works. It's a cyclic process that you try something and check on it, and then you just make a decision about it, and then you start over, really, so can become kind of a cycle. And this is just illustrating the difference between exploration and optimization. Pure optimization just tries to find the one best solution, and like I said earlier with the linear programming, it does that real well, but it may not be the solution you want. You may look at it and say, oh yeah, but that doesn't work for some reason, that wasn't included in the original description. So that solution's there, and you'll see it in exploration, but you'll also see a whole range of other solutions. So you're able to, the idea is it's supposed to inspire you or give you a little bit more of a scope of the possibilities in the problem. And in early design, that's what you want. You want to be able to explore different options. So this just makes a comparison. This is trying to make the argument that GAs genetic algorithms are particularly well suited for this kind of exploration. They use populations, so you're not looking at a single solution. Operates in cycles the same way as design tends to do. There is a certain amount of randomness in it, but you can control that. And it's not really deterministic in the sense that it's not like the linear program that's determining strictly determined by the thing that you're optimizing. Okay, so this is the method that we use. It's based on a NDDP GA, which is a non-destructive dynamic population GA. And it goes through a cycle. Maybe you could imagine it starting with a pair of solutions. It breeds those the same way as you saw earlier with a crossover of some sort. It breeds the variables. Then you have to put it through some sort of a parametric software that takes the variables and converts it into a solution. So in terms of architecture, you're taking the variables and turning it into a form, right? This may be Grasshopper, that you can plug a bunch of variables into. What's the one in AutoCAD now? It's got Dynamo or Dynamax. I forget. Dynamo, I think is what it's called, is AutoCAD's. The earliest one, at least that I used, was Bentley's Generative Components. That one's kind of been left in the dust by Grasshopper. Has become so super popular, but that was also one. So, and you can do it. You can do it with an Excel spreadsheet, really. I mean, there's a certain, that's also parametric. You can change variables, and it changes through the. Anyway, so you get some sort of a solution here, right? And then you have to evaluate that solution. This is the evaluation, and that can be any form of evaluation. Of course, in my interest is structural evaluation, so it usually goes through some sort of finite element program and finds all the forces and sizes members, that kind of thing. But we've also done them where it does lighting analysis, acoustic analysis, cost analysis. So anything that you can analyze. In fact, with this method, it's also possible to do like an aesthetic analysis. It takes more time, but you can generate solutions, and it'll make like an array of 10 solutions, and then you as the user can physically pick the ones that you think are the best aesthetically, or whatever other criteria you're that you're able to see in it, and it'll produce a solution. It will continue like that. So we've done a few like that. It takes that solution then, along with all its performance values that are calculated, and loads it into a SQL database. And this is kind of the nice part of it, or it was originally kind of the innovative part of it, but now there are a lot of programs that more or less do this. In that everything is maintained in that database, and once it's in the database, you create the database like this. And once you have that database, there are all sorts of tools that you can use to search that database and find instantaneously different solutions. Like you can say, once you have the database, you can just sit down and say, okay, what's the lightest? Boom, the 10 lightest solutions come up. What's the, and have combinations of variables as well. Anyway, from that database, then you make your selection somehow and continue breeding then. And then you can see it's a cycle that essentially builds that database. Compared to the way it used to be with the original genetic algorithms, there was no database. There would be one generation, that generation would breed and produce these children. So these two would breed and they'd produce these two children, like that. Then you'd look at the combined, the parents and the children, and you'd select based on some criteria of fitness function, you'd select the best ones. So here it's selecting these as the best solution. Some of them were the original parents, some of them the children. Oh, the children are doing better than the parents. So it selects, half of them, enough to fill a new line of parents. The ones that aren't selected die off. They just disappear. They're not maintained in a database normally. So this is what I mean by it's a destructive approach. They are lost. And the idea is you continually get better and better solutions. It does work. You get better and better solutions, but it has a few disadvantages. In losing these solutions, if down the line here, these two go together and create a solution that's actually exactly the same as a solution that we had up here maybe, but it was lost, you've got to you don't know that it ever existed before. So you've got to reevaluate it. And that's in terms of just efficiency, it's very inefficient because you have to keep, and this originally was a big argument with genetic algorithms. Oh, they're just so inefficient because it takes forever. You got to keep going through these because you're reanalyzing solutions multiple times because there's no memory of it. Well, when you use a database, all the solutions are maintained, so they're all in there. And what you do is you select. There's some selection process that picks certain ones and puts them into a population that then you use to create the parents and breed a child. And once you've got the child and it's all analyzed, it goes back into the population. But there's never any loss here. That the population, even if it's a not so good, it wasn't so good, but it's still there. And the advantage of that is, if I breed two parents and they come out with a child that already existed, I can immediately look back here and I say, that child we already done that one, forget it. And then you go on and immediately breed a new child. You don't have to repeat things. So there's an advantage of that. The other big advantage is you're able to look at all these solutions and you can look at them under different microscopes, right? You can change the criteria of what you're looking for, and you can search that database pretty effectively. Okay, so this is some of the advantages of combining a GA with a database. So, yeah, I think in looking at it myself, I decided there were 7 advantages, or at least 7 I could think of. And one is what I just mentioned. You never have to store duplicates. The database, it's very easy to set a parameter on a database that immediately, if you have a new solution, it immediately sees if that solution already exists, and if it already exists, it does not allow that solution to be entered into the database. So there's a very easy, the unique index allows you to make sure you don't duplicate any. Okay, so that's good. So that reduces the analysis time because you never have to repetitively analyze the same thing. There are no duplicates. Okay, it gives you better graphing because you're not graphing the same things. And of course less storage space. I guess that's a little bit of an advantage too. Another advantage, it can be you can very easily accommodate multiple objectives. In some instances, this is kind of difficult to have. I mean, it's very easy just to have one objective that you're focusing on, but as you increase, you say, well, yeah, least weight is good, but also I want to consider cost, and I want to consider floor space, and I want to consider, the more considerations, the more objectives that you enter into the problem, it becomes increasingly difficult. And it's also, I guess, when there's no database, you can only look at one at a time, really. I mean, it's difficult to change which one as the program's running and optimizing, to suddenly say, oh, I want to optimize for something else. Well, it's like, well, then you got to start over, basically. But with a database, it's very easy to set up search functions that you put in the variables you want, you put in the range that you want, you put in, it's greater than, less than, equal to, and so you can, you have a great deal of flexibility there in how you search. Okay, the dynamic populations, of course, that has to do with right when you make the selection of the population's not being bred. It's not like there was a population and the children came from it, and then I create a population, and then there's a new it's not progressive like that. There's a pool, and I can instantaneously pull anything out of that pool, which means I can instantaneously change my fitness function. I can have the two different parents each have a different fitness function. I could say, I'd like to say parent 1 is least weight, parent 2 is least cost. I'll compare those two and breed it and see what children come up, from those two extremes, the lightest solution and the cheapest solution. Let's see what those two produce. And that, you can do things like that with this when you're pulling the populations out of the database, which otherwise is not so easy. The other thing you can do is you can search that database dynamically in any areas. And this, not only you can search it in terms of breeding new solutions, but also you can just look at the solutions instantly based on any of the criteria. So you can imagine you've got a range of solutions, and depending on what I type in as a search criteria, I can look at that part, or I can look at that part, or I can look at this part. And I can use this, I can make that the part that then breeds parents. I'll get two parents, and that allows me to focus on that part of the population. So it's like I've got a range of solutions, and I can focus my attention on any part of that range, right? And I can generate more solutions like those, or I can just look at those and see what they're, what kind of solutions are those, and which is, helps you think about the problem too. It's also interactive, meaning that you can view this database. You can physically see. I mean, because of the field that I work in, there are buildings you can look at, right? I mean, the structure, you can see it. So you can generate an image of it. You can generate different images of it. Like with the structures, sometimes I'll generate a deflected image, or generate the moment diagram, or generate the axial stress diagram, something that would be significant to what I'm looking at. And then I can compare those visually and see the differences, and that teaches you a lot. That's what I was trying to do at the beginning of class, right? You look at all those solutions, and if you think about it, you can start to see the rationale. It teaches you about the problem, really, what's going on, because that's ultimately what you have to learn about the problem if you're going to be the one that solves it, right? The first step is learn what's going on with the problem. Okay, so these are just different, you can see the visual control, and this business up here at the top, this is what actually controls it. You type in limits and different things to search for, and then it displays what you're asking for, basically. It also, since you have all that data in a database, it's very easy to graph it in different ways. You can, graph it with traditional XY graphs, so you can pick any two variables and compare those and start to see, how they, where in this case, this was weight, so here are the lightest weight ones. This was stiffness. These are the ones that are higher frequency would be more stiff, right? So higher frequency. Then let's see, or these are parallel coordinate graphs. Yeah, I've not, to be honest, I'm not an expert with these, although it generates them. You can see each of these is a variable, and you can see then if you pick, you can see some of these are darker lines and some of them are lighter lines. You can pick a certain variable and it'll plot all the solutions that are using that variable. So you can see, for this guy, they're also, a lot of them are down here. They tend to be lower there. They tend to be the higher ones here. It's not looking at that, not looking at that. So starts to show you which variables go together, I guess, is a use of that. The other feature that's in this, you can, if you click on any dot in the graph, it immediately will give you an image of that, which is kind of nice. So you can, when you're trying to make decisions, you can look at the graph and say, oh yeah, what's this one? And it'll immediately show you what that is. So that's kind of a handy. I mean, I'm trying to build in things that connect the data with the image, so that you see the image. And so this is the same thing. You can pick. This was one of our doctoral students was working on a tower design based on these irregular framing things. Yeah, this is what I mentioned with the parallel coordinate graphs. And Pareto optimization, my favorite. You can, when you graph these, if you have two generally opposing criteria, then you're looking for a trade-off between those. So it might be, the most obvious is weight and stiffness is always opposing, it seems like. As you make it lighter weight, it gets less stiff. As you beef it up, it gets stiffer. Well, but you want one that is stiff and not so heavy. So it's they're opposing criteria, but you want to find a good trade-off of those two. This is weight versus the stress, von Mises stresses. And when you graph those, there's a frontier here. The edge, these out here are the what they call non-dominated solutions. In other words, if I pick a solution here, there's no better solution. There's nothing in here. There's no better solution than that one. Or if I pick this one, there's no better solution there. It's not true with this one. If I pick this one and I say, whoa, there are a whole slew of solutions that would be lighter weight and have a lower von Mises stress. So see, that's why I'm trying to get reduce those two. So these are the best solutions, and you can see some of them are extreme in one direction, some of them are extreme in the other direction. Usually you want to, as a trade-off, you want to be somewhere in the middle. But you'd like to kind of see what the trade-offs are, too. You can also do this in 3 dimensions. At least I can graph it in 3 dimensions. So you can get, here I've got von Mises stresses, deflection, and weight. And, I can look at these. These are the ones that are on the frontier. They're actually sets of these. You've got the absolute frontier, and then you've got one step behind that and one step behind that. They're different, like if I make it, there are 2 that are in the way, that it's 2 behind or 3 behind. So that's what That's what these represent. You can also, so you don't have to make it, if you're using this for breeding, they don't have to be the absolute best ones. You can say, yeah, within a range of that perfection there. You can also do it in actually any number of variables. I just can't plot it. I've not figured out how to plot beyond three variables, but you can, mathematically, you can do it for, optimize, find the Pareto set for 4 or 5 variables or more. Okay, and you can use that as the breeding set, so it's actually something like that. And this is all, can easily be run on parallel hardware. So we've done it like, this was the old lab we had. You just start up each one of these machines. As long as they're connected to the internet, you've got a server that's holding the database, and they just have to be able to send their results up to that server. So you can have any number. I mean, they can be all scattered all over the world. They don't have to be a lovely cluster like this. As long as they can connect to this central database and upload their solutions and download new parents or whatever, you can do that. Okay, so those are advantages. What this is sort of like, at least I kind of imagine this. Google Maps is also a database, right? I mean, has certainly the map, but you can look up all anything you type in, stores, products, they'll show you where it is on the Google. So they got a huge database, and they allow you to search the planet basically for these things. So if I'm located here and I want to find the closest pizza to me, I can type that in, and Google Maps will show me where the pizzas are, and I can find the closest one or find the most convenient one. Well, what we do is a little bit similar to that. It's also a database, and we are trying to project a map of that database, and you can put in your criteria, and you can search for different things in that space. Kind of. At any rate, that's my analogy there. Okay, this is we kind of looked at before, the cycle that it actually goes through. I guess selecting one, breeding, growing, and these can be. You can use a variety of different software. The method remains the same. It's really what we came up with was a method, but you can plug in, like Grasshopper. You can use what was the other one I mentioned? Dynamo. You can use the generative system, Bentley's, whatever that's called. So any number of different components, or also to evaluate. There can be a whole list of and they're not limited to one. You're just collecting information. So I could run it through STAD, and then I could run it through something else, Ecotech, and get information, solar information. I could run it through some sort of cost analysis and get the cost. So you're just collecting information that eventually gets placed up into the database. It gets uploaded to the database. Okay, so this goes through the steps. Yeah, selection, like I said, is normally done by you select the variables that you're trying to optimize. You create a fitness function, and that can be fairly complex. It's essentially a query. You're writing a query that goes to the database. So any query can be, between a range. It can be any number of variables. You create that query, and that pulls out the population, and then you randomly select parents out of that population. So you can limit the size of that population, maybe make it the 10 best or something, and then you pull parents out of that population. You do have to leave to leave a little bit of randomness in it, so that you're not too deterministic. That there is a possibility that you'll generate something that you're maybe not specifically thinking of. You can also do this, like I said, you can pick a couple of them by just clicking on the screen. They'll show up here, and then you can breed them, and it'll breed a parent and breed a child. Breeds the two parents and gives you a child. It'll give you a child, and then you can analyze that. So you can do it either way. I mean, normally it runs automatically, but there are some situations where you kind of really would like to see two particular, concentrate on just a couple of them. This is the breeding is half uniform crossover, which means you take all the variables and half of them come from here and half of them come from there, and they get put together. And then some of them are random. Which ones are random? I guess the yellow ones are random, right? So these are neither from, oh, well, no, wait a minute, I'm not, oh, this one's directly from there. It doesn't get, these two are bred, so the yellow ones are being bred, and these come directly. And you can also, on top of that, you can introduce a certain number that may be random. Usually the random ones are kind of not so often. You don't have too much randomness in it. Maybe at the beginning, or at the beginning you can have it. Actually, yeah, I take that back. At the very beginning, it's totally random, because you've got to generate the initial database. So you may run, 100 or something. They're just totally random generated until you get you create a database, and then you start picking them out. But initially, you've got to have that pool, and that pool may be randomly generated. So let's see. Then this is just this would be what you get from the child, right? These are the genes, so to speak, and those genes then get plugged into this is generative components, get plugged into some program, Grasshopper or whatever, and that generates parametrically the form. And then once you have the form, then you analyze it with whatever. And this was Ecotech we did a lighting analysis on some. And then once you get the solution, you can capture any image. There's the data from the solution, right? The actual performance data. But then what's also important or useful are the images. And you can capture any image as you go along. And also you upload that image, and it gets tagged to in the database, so that that's what you see then when you are visually looking at it. You see an image. You don't just see all the data. You can see the data too, but the image is usually a little more descriptive. So these are, and then you can search it once you have it. Like I said, these are all just search criteria, and there can be any number of them that depending on what you've collected. Yeah, this is just looking at the graphing again. And a few examples. Okay, yeah, we even have examples. Time for a few examples. This was a fun one. This is one of my favorite ones I got to do. Vladimir Shukov was an incredible engineer, and he did these structures early. Oh gosh, when was he? I should put the date on here. It was like 18 something, before the revolution, and he built this tower. This was one that he did. It was a small water tower, but also what was for a long time the tallest structure in the world was a radio tower in Moscow, and it's still standing. I think there was a danger that they were going to tear it down, and then there was a big uproar worldwide. Oh, you can't tear it down. And I think they did save it, but it was the tallest structure in the world. Just it kind of looked like this, except it was stepped, I think. and held originally a radio mast. Anyway, so we took his water tower and we thought, hey, let's check it out. We'll optimize it and see how close he came to an optimal solution. So we set up the variables. We had variables for the number of members. We varied the base and the height diameter. I mean the top. Maybe the top was set. I think the top may have been set because this weight was set. Was a certain weight that was put on it. And then we ran quite a few solutions and graphed it. This is the weight versus displacement, and this is actually his solution. That was what Shukov came up, which was almost perfect. I mean, it's right on the Pareto front, right at the best. So it's kind of amazing. I don't know how he did it. Probably with models or something, but or just had very good intuition about it. Knew what he was doing, but it kind of bore out his work. And these are some other ones we did. We did some domes, looking at different mesh configurations of domes, and put like a wind load and gravity loads on them. These are just looking at the different mesh configurations. This was one I did with a guy. I don't think this actually got built, but he was looking at soccer stadiums, and for soccer unlike our football fields that have artificial turf a lot of the times, soccer requires actual grass. So you've got to have, usually they have an open oculus to let the sunlight in so that the grass grows. So this was a comparison of the size of that oculus versus the height of the dome versus the curvature here, and trying to find obviously structural criteria and least weight and that kind of thing, seeing how they'd compare. So these were different extremes that we, some of them could be slightly inverted. Oh, there goes my pen. And we generated a whole range of solutions, and then he eventually we also looked at the stiffness. This is modal analysis, so this shows the vibration in terms of stiffness. So some of them, would be much more stiff than others. Others, the amount of deflection is giving you some idea of the stiffness. Okay, and then this was another one I did with some students here that was purely based on visual criteria. So they actually did build this. It was a little project they did. They wanted to have a reticulated surface structure. They had the joints figured out, and they're going to build it. And they wanted it to be stable, so we generated some that were, in the generation of them, they were stable. We did that kind of like a check to make sure they were stable. But then the other criteria had to do with how they were going to build it. And what they did is it would generate whatever this is, a couple of dozen at a time, and they would physically pick the ones that they liked, and they'd pick like from any set less than half or half of them, and then that would get put into the next generation, and it would cyclically breed like that. And you still maintained all the solutions, but it was just showing you the current set, like generations, and it was limited. I guess they set, up here what they were looking at, and but they would just visually pick it and breed it. And in the end, they found one they liked and they built it. So I guess it kind of worked out in that sense. These are some other ones we did with Michaela, who's at TU Delft, and Falk, who's up in Denmark. And this was a tree structure supporting a plate structure. and it was the main criteria. We did look at the optimization of the trees, trying to reduce the weight on those or make sure they were sized for strength. But it was mainly looking at the sun penetration and trying to get a certain illumination on the interior. So that was this map was charting the solar exposure underneath this thing. Oh, it had to, right? They had to be open. They had to be opened to allow ventilation at the peaks. So it was kind of a complex thing, but that was what that was about. And this is looking at the different solar. And then this is one we did with Ted Hall, who's across the street. This was a structural analysis of a geodesic dome, trying to find the best for a given diameter, and this was a snow load that we placed on it. Actually calculated the snow load based on the angle of the plates, and then looked at variations of geodesic domes and tried to find the best structurally better solutions. So that was that one. This was one we did here in Detroit. It was kind of a weird one. It was they had already kind of decided on this structure, and they wanted to analyze the fabric that was going on it, that it was supposed to have a certain orientation. It was also had solar cells or something on the fabric, and so we were doing lighting analyses. It had to have a certain amount of curvature to stabilize the fabric, but then it was also that red and yellow is trying to find a maximum solar gain from it. And then the last one I can show you, this is one we did here. It's actually wood, even wood. We did here a couple of years ago, where some faculty members that were looking at utilizing tree crotches. So these are, in the harvesting of trees, this is junk. You know, it's normally almost not even usable for firewood because you can't split it into usable logs. So it usually just goes to the landfill. So they wanted to take these and use them as the joinery elements in a reticulated shell structure. So these were kind of given elements. I mean, they harvested a whole series of them. We put they were actually the angles and the shape of them was entered into a database, and then you had to pull those joints out of the database, make them into the structure, and then you could analyze the structure for the height and the openings and the different. A lot of it was also visual and structural. So this was these are what the pieces look like. We took this raw lumber, I mean the crotch, and that would be mounted in a little thing that held it, and there's a 5-axis router downstairs that shaped it. So we could get the ultimate, this is been shaped from the original crotch, and then they were used. Whoops, where'd it go? Then they were used like that in this structure. So this was the game. You're given these, right, and you're given the. I think there was a variable. You could have variable lengths that connected them, and they just pinned together, and you had to create this form. And then this is the bending moment, right? This is the axial stress, and this is the load that's on it. So we were trying to minimize the bending moment, but ultimately had the limits given by the members that we were using. So there was a capacity limit. And then these were some of the forms that were generated. And we look at, let's see, I guess it was trying to minimize the out-of-plane curvature. Okay, and the bifurcation angles had to be between that range. It minimized the number of joints. It gave a smooth surface as best it could. We were looking at the entrance and the center height. These heights here, that versus the total height, and there were set limits that we put on those. The weight and member forces and deformation. So all those things were variables that we looked at and used to eventually pick one solution, which I think that was probably the one that we went with in the end. Fit all the criteria that we had, and then we were going to build it. By the time we figured this all out, there was only like 2 weeks left to build it. And although we could have built it, the slowest part is machining those joints. And that took like, I don't know what it was, 6 hours per joint or something. It was an incredible amount of time to mill each of those. And that limited the number of joints that we could produce. So we didn't do quite the full structure. There's a picture of it at the end, I guess. This was the, for any of these, I didn't say that earlier, but you can always click on these images and you get a full set of the data that goes with it. So this is all the data that we collected that was used that we could look at. This is how we actually, I guess we did graph it and picked one that was the one that we actually built. And then this is the 5-axis milling machine. And this is the actual built section. So we cleverly built it so you can kind of see it. It might have been mirrored in the windows, but we were only able to build a third of it. But we did get that much up. It was successful as far as we went. At some point we had to take it down, and we decided, well, hey, it's got to come down anyway. Why not load test it? So we actually did a load test till failure. And these are water buckets. So you fill each of the buckets with water, and you pour the water in, like a quart into each bucket as you go around, and then you can progressively increase the weight until it fails. They're also deliberately hung only a little bit off the ground, so when it does fail, that it immediately unloads. You don't have catastrophic failure. It just breaks. At least that was our hope, and is in fact what happened. There was one. I don't know if this picture is it. I think this was still just loading it. We were still loading them at that point. This was the load that was on it, and this is where it broke. There's the one that broke. So that was it. Oh, we loaded it with sand. I'm sorry, I thought it was water. I guess maybe we started with water. It wasn't heavy enough. We went to sand. Okay, so that was then we were able to determine the maximum load was 70 pounds per node. Carried that, which was a pretty good load. Would have been more than snow load anyway. Okay, so that kind of gives you an overview of what you can do with optimization. It'd be fun. I'd love to actually, the other day, a week ago, I was thinking, I should do this with the problem that you guys did. But then it's a busy time in the semester. I'm sorry, I did not. And it does take several days to set it up. That's a downside with this too, I guess. You've got to write the different program. I mean the Grasshopper script, and then there's a script that ties it all together, because you realize when this starts, it's hands off. It just, you go home and go to sleep, and you come back the next morning and it's, run. So that means from the downloading to the generation in maybe Grasshopper, to the evaluation maybe in STAAD, to the collection of the data, collection of images, and uploading, all that there's a script that you have to write that controls all that. And writing that script, that takes a day or two. I mean, that's a bit of work to get that all put together. So it's not something you do just like that. Actually, Grasshopper has gotten some good components now. They've built in Karumba, which does the finite element analysis inside of Grasshopper, so you can combine, the initial form generation and then the analysis, so you can almost do it entirely in Grasshopper. I think and Grasshopper has built-in genetic algorithms, so you can use that too, I think, in it, but they're a little bit more limited than what I've got. And it, I think, I don't know how, it probably doesn't have a full database, not really a SQL database that you could store everything in, but, so it's not as flexible, but you could do an awful lot of it just in Grasshopper, is getting to the point. Anyway, fun and games, huh? Okay, so that's that, and next Tuesday, it's your turn, right? Not your turn. I didn't mean your turn. I meant your turn. Somebody out there. Hopefully you've all signed up, and do look at, there are different things that you're supposed to submit that's depending on your group size. So if you've got a group of 2, everybody does the presentation, and you will submit a model, which you've already got. You've got a physical, so you're good. If you're a group of 1, I think all you have to do is the presentation, if I remember. If you're a group of 4, you've also got to do a poster, or a physical poster is probably the easiest thing. What we usually do for posters are just 11 by 17, like 3 sheets of 11 by 17. Is much cheaper to do than a real poster. So if you're in that category, you can do that. It would be good, I think, we should probably plan on, rather than everybody bringing their own laptop and switching out, if it's possible, if you can put your presentation on a little stick, we could just use my little guy, and that way it's already connected, and all you've got to do is plug into it, and it should project everything okay. So either a PowerPoint is what I've always been using, or a PDF. Obviously you could do that. I think that would probably be the best 2 options, right? Okay, should be fun. All right, well, have a good weekend.